Welcome everyone to another fun, are we live? Should be live. Fun FPGA live stream, of course, as usual. Not only Linus Tech Tips, technical difficulties with used YouTube beta, but it looks live, although it shortly did not look live. But anyway, so yeah, the recurring viewers might remember we did here some video Verilog stuff on the icebreaker FPGA here of 1-bit squareds and open source, Clifford Wolf and all those people there, amazing people, having done also reverse engineering, so we are having fun with their amazing open source Yosys next PNR toolchain. And this took way too long, by the way. Is this cool reflection somehow in the lens? I guess that looks actually like anyway, so this took way too long, and this is also why I didn't live stream it. It's probably better that I prepare the stuff a little bit. Let me just also wrong. What took so long? So it took enormously long to figure out, just move the camera here 1 second, how to combine this with a PicoSoC. And the issue was that the design was optimized away, so my video design, the Verilog, worked freestanding, and as soon as I combined this with the PicoSoC, my entire design was more or less optimized away. And that is obviously not helpful if your design is gone. And yeah, it took multiple days, even ask for help there at Clifford and all the other people doing that, and only today, after putting even more work into this, I finally got this to work. Let me show you. A little bit different. There's always the videos, always something new, something different. So here is that view, and as you can see, we have here this the stuff running. And also, you have seen the previous video while I was traveling on the previous video capture. This was not as amazing, the video capture here from this Epiphone. Actually, no, this wasn't the Epiphone. Sorry, as it was a cheap Chinese. But anyway, on the previous video where I had this text mode stuff working, if you're interested in all the details, previous video, because if I repeat everything, this video will be 5 hours. But as you can see here, so this is not fake. Do we also probably haven't manual refocus this? Totally relatively amazing graphics. This is 640 by 480. We are only limited, or mostly limited, with the memory here, especially as we want some memory left for the Pico RISC-V. Darn, quite some drop frames for some reason. Anyway, so as you see here, really nice sharp text. We have some small issues left, like the text because of memory access delay that I did not yet compensate for. A little bit more learning experience and such. Something for another day. And otherwise super sharp text, except first pixel off by 1, and also the colors is like, I think the text is like 1 pixel off by 1, and the colors might be 2 pixels, but that doesn't even matter. Actually, by the way, it is full with relatively random gauge, because I was testing. So this is intentionally that it's actually not random. It's graphic data. I was also working on supporting graphic mode fully again. So all of this as expected, except 1 pixel off by 1. And now, as you actually do not see, let me show you that combined here with actually some screens. So at the same time, we have here, screen is terminating, what? We have here actually this RISC-V fully running. So this is a serial console to the RISC-V stuff. So that is RISC-V, Pico RISC-V from Clifford Wolf. And so the open source stuff, I've not written this, but we will soon add our own firmware and do some fancy text and graphics, and then also add keyboard, mouse and sound another week or month. And as you see, the stuff here is fully running. So memory test, for example, or the toggle here is run simplistic benchmark. Was this 9 or yeah? So cycles and stuff. So this is a RISC-V, Pico RISC-V without MMU, bare metal level firmware running. And next, let me just camera scenes and stuff. So what were the stuff? Let me first say. So as I said, what is missing? Next will be actually interfacing this. Right now this is static in the memory, and a full text mode, theoretically also graphic mode, not so far off, with a fully programmable color palette of 16 colors, and here's a mouse cursor and 16 by 16 pixel, what we've done on the PS3, the Octane or other vintage stuff, that we have a pixel precise, like a sprite, that we can not need to do this with a CPU, but have a nice overlay. Quite some fancy stuff, quite some Verilog, some 100 lines of Verilog, really nice learning experience. And the only thing missing is actually implementing bus logic so that we can, from the Pico RISC-V, write to the memory, the video memory, and actually alter this. That will be next. Let me show you what were the issues on the way that you learn something at home. If you want to join this here also, this is now online here somewhere. GitHub, on my GitHub, if you want to play along at home and also work on this. So help if you want to fix this off by one text character set or this off by 2 color palette stuff. Be my guest, send me a patch or pull request. That is here, Pico RV32. Hope I also show it. This stuff is now online. Just pushed this here some minute ago. And here of finally working PicoSoC plus VGA. If you want to take a look on the commits and the actual code. To show you what was not working, so the VGA module was working before, and to explain to you here in summary the 2 issues that took the longest, which probably also we could zoom out here for maybe slightly improved visuals. The one roadblock showstopper was actually having the synthesized, meaning also this detaches screen. So when we run here make icebreaker, of course right now this is up to date. So normally that would synthesize quite a while, like compiling from the Verilog. So this even on the Ryzen, so this is right now the Ryzen 3950X, but this is mostly single threaded, so yeah, that's only helping partially. And when we take a look here, how many drop frames? Quite some, whatever is this. Docs is really fat. You see this synthesizes quite a while, and the issue previously was that, and again, mind you, right, our simple VGA stuff, even on a Mac Mini, this just the video core synthesizes in maybe less than 10 seconds, but this huge RISC-V, there you see synthesizing a real, real RISC-V CPU with all the SoC, the system on chip stuff, takes you quite a while even on Ryzen. And the issue is that I added my design, this VGA core stuff, to this PicoSoC, and it disappeared. It was optimized away. And I think in the meantime, because the issue is here is the module with its inputs and outputs, and this is also new. This is a memory bus, the I/O memory bus that we need to do next, but this also doesn't yet work. You see everything here takes quite a while of research and development and getting started and learning curve. Previously this was freestanding, and the issue is that I added this to the PicoSoC here, and this didn't work. So we have, for example, the simple UART that was already in the design, and here simple UART, similar to this, we have now VGA stuff, and I just added this similar to that, and it took me hours and days of on and off. And I think I'm not yet entirely sure why it was optimized away, but I later figured that this is not the main module. There's always a top module, top top of the design, and this is the icebreaker here. And then I thought, maybe, wait a second, maybe it has something to do with that. And I then removed this from the PicoSoC and moved this code over to this icebreaker top Verilog design module, and this worked. So we now have here this output. These are the pad outputs here for the PMod, for these modules here. This is even on camera somewhat sort of. So these pads here are those pins on the PMods. And then here also VGA. So this is an instance of our VGA module. You see this I/O memory stuff is new, coming next, and these are the HDMI PMod outputs. And so this looks exactly the same, just that it works here and doesn't work in the other. Most likely, maybe because, probably now that I think about this, most likely because that you learned something. Maybe this would even work in the PicoSoC, but it makes more sense because PicoSoC is like basically this tiny system on chip design. And I had here outputs. So most likely the issue is that these outputs that I had here were not connected. But it makes more sense in this icebreaker anyway, because this is actually the board definition that we are using. So it makes more sense inside this Pico, in this icebreaker top module, because this is just how we configure our board anyway. Maybe now that I think about this, maybe it would have worked if I would have just connected the outputs here in the PicoSoC, because the PicoSoC is also instantiated, most likely. So thinking about this, most likely it would have probably worked if I would have connected this P1A1 or what it is to the P1A1 something. But anyway, in the meantime, I don't even want to have it in there anymore. So it was just that I thought that this name of the pin would match this connection, but it doesn't. So this is purely design module parameters, so most likely this is why it was optimized away, because it wasn't connected to anything. But after this, so this took multiple hours of trial and error and research and learning curve. Welcome everyone, by the way. Merry Christmas again to everyone tuning in here and later and such. So with this, so there you see it looks so simple, and yet this kind of also, because you don't get an error message, it's just like it's instantiated, it's synthesized, just like optimized away. And if you, until you gain this experience and learn all this new stuff and understand what's going on and where you need to look at and why it's happening, then the usual 10 and 90%, 10% of the smallest integration stuff take 90% of the time. The second issue, so after this it was still not working. I got an error of PLL could not be connected. Don't really have it here right now anymore. The issue is, this took me also another hour or two to figure out, because previously I had this PLL, this phase locked loop for the clock generation. For the video core, I had this obviously in the video core here, VGA, and this didn't work because I didn't know, and I couldn't even imagine that. The issue was, I have here the clock. This is a 12 megahertz main clock of the icebreaker, and this clock here was of course driving this PLL. So of course we have here package pin clock. PLL is a phase locked loop to generate other frequencies, and we use it here to generate 25 megahertz for our 640 by 480 video signal. And the issue again was just that could probably theoretically maybe, what do I show? The problem is not want. If you're interested, or actually I rebooted. Sorry, rebooted in the meantime. Not because I don't want to expose some private Twitter chat. Anyway, people's private coordinates. But so the error was something like I cannot, like next PNR was something like error PLL could not be connected to some pet something pin, whatever. Again, took me super long. So the issue is this PLL needs to be a directly connected signal. You cannot drive it, I don't know why, for routing reasons whatsoever, something. And this took super long. I asked Clifford. Also, of course, when I ask people like Clifford or others, I already Google an hour or two and like get here crazy, like why the freaking heck is this not synthesizing? What the heck does this error message even want to tell me? And in total, this took me like literally 2 hours, and I even asked on Discord here. Do I have it still open? Maybe not. Here I have it open. Yeah, here. So TNT there. Huge shout out there to TNT who helped me with this. And this even I understood that I have some global buffer, but other people also have this issue. So this is my code. Other people also have this issue and Google around for hours. So it turns out there are multiple modules here. So this is this SB. This is, by the way, do I still have it open here? User. Maybe not. Where would it be? I think SB stands for something blue. What was this? Let's just quickly grab this in user share ice box maybe, or uses something. Here. I guess here we might find this, and yeah, Silicon Blue. So I think SB stands for Silicon Blue, which is a company who created this before Lattice purchased it. So I guess at least that's what I think it stands for. If that is wrong, correct me down there in the comments below. So I knew I need some kind of global buffer. So what I also spent from this 2 hours of getting this PLL working, I spent like half of the time trying to instantiate some global buffer to buffer this clock signal. Because again, this could not be connected. The issue is this clock, this 12 megahertz clock, we need this clock to drive our PicoRISC-V, and we need to use this to drive our PLL for the video signal. And I tried there with SBGB, like GB for global buffer, and GBIO for global buffer IO for 1 hour of Googling and trial and error, synthesizing an error and whatnot. And then in the FPGA Discord there of Icebreaker, TNT helped me out for using this. There are pre-made modules, 5 primitives. I was using from this video example that I based upon this. Was it Silicon Blue? No, I forgot already what this stood for. Silicon Blue. This SB Silicon Blue PLL40 core. And this primitive should be used when the source clock of the PLL is driven by the FPGA routing. This is the simplest kind of PLL. Can be used universally, but as we know, it's not the best choice for the black eye something board, whatever. So then there are multiple modules. Underscore pad should be used when the source clock of the PLL is driven by an input pad, and the source clock is not required inside the FPGA. And this is exactly our issue, right? We need the source clock also additionally inside our FPGA. And so there's also this _2 and _2f. So the difference is that the source clock of the PLL is driven by the input pad, and additionally to the PLL output, the source clock is also required inside the FPGA. So either _pad or f_core. I think what we are using now 2 cores. So the difference is this is the original. This building block is wiring out the original clock signal, and the difference is this one is generating 2 frequencies. If you need another frequency, for example, we could probably use it to clock our RISC-V faster. So right now I think our RISC-V, PicoRISC-V is running at 12 megahertz, I guess. And if we can maybe clock this faster, we could also use this to generate like an 18 or 20 megahertz clock, for example, another day. Anyway, you see, these were the small things. Now, what I do here, correct me if I'm wrong, but maybe we are doing something stupid. But something like this is what we need, and we have here now wires, this kind of signal wires inside the FPGA, and the pixel clock is what we are routing into the VGA module, and this clock 2 is what we generate as the copy of our clock signal. And you see we now use this _2 for, or using the original frequency PLL. So package pin is the input to the package, the clock input, and then PLL out core A is the copy of the signal, the clock 2, and PLL out core B is our newly generated signal. Previously this was just core, and now we have core A and core B, A being a copy and B being the PLL phase locked loop generated pixel clock signal. Due to that, I now changed here all the icebreaker PicoSoC setup to use this clock 2, which is the copy of our signal, and the pixel clock is what we are supplying here. So I also changed the VGA module here, obviously, to receive the pixel clock. Previously this module was generating it, and now we are, because this is a little bit unfortunate that we need to generate, we had to modify this icebreaker, but that's what it is, because we need already this icebreaker module to have the system-wide clock signal for our SoC. So that's it for this summary. We have already some comments. Jay Tanciante says, I know it's a bit unrelated, but there's a bug in Popo. If there is some program, this will run CPU 100%, eat all the memory, freeze your PC, something install just now. Okay, amazing stuff. What is next? So even the next thing, you could think it should be simple to just extend this. You see I already wired here this I/O memory stuff, but here's the next challenge. So because I tried here already, so what we need to do next to use our software, our code running on the Pico RISC-V to actually write into the memory, we need to connect this to our memory mapped I/O bus here. The issue with this is, it always sounds easy, the terms that we know from AMD and Intel and VIR and ARM spec sheets. It always sounds simple, like just some address matching logic here on positive edge of clock. I copied this from the PicoSoC, I/O memory valid, and I/O mem on, if not, so if I/O mem valid, not I/O mem ready, which by the way, I think previously you might have I/O mem ready. I need to check anyway. So what this means is, if I/O mem, like access from the signals generated by our Pico, our CPU core, if I/O memory valid and not yet ready we set ourselves when we process this signal here, when not yet ready and I/O, when this top level address, I changed this here to 8, this is our mapping of our video memory here, our whopping 32 or something, whatever large we can make it. And the issue is when I enable this code, and you will see how long this, actually we could check here. So I copied this I/O mem here from this, here probably from this, GPIO. And so here was ready, so we maybe want to assign this ready here too. So I probably should be relatively good. You will see, so make how long the synthesizes even on, we get already warnings. And this is exactly the issue, that we now have multiple drivers, meaning I/O mem ready is assigned in block at VGA and GPI. Right, this is even a signal. Anyway, so the main issue is assigned in block something and in well, let's first, this is not right, we don't have a GPIO here, this is implicitly defined, we don't want this. This was my mistake. But the issue anyway is here multiple conflicting drivers, meaning we have two sets of logic that is driving this IO mem ready stuff. And excuse me, did I mention it's winter here and I had a cold? So you see, even the most small stuff is difficult. We most likely need some bus multiplexing logic. My idea was, because right now this is only used for the GPIO, my idea was actually to say goodbye to this GPIO LEDs for a test, like layer whatever. Don't need this blinking LEDs here, and see how much this works. This probably IO mem ready is assigned in the block is implicitly what the heck GPIO. Ah, here is also our data. Do we have this there? This is as I said IO mem. The input is IO mem valid, meaning this address lines are valid. IO mem ready is our output when our output is ready, and this is write string, or I don't know, write whatever byte, and which, by the way, data, not sure, write data, read data. Why is this write string byte? Not sure. Why is this wire? Maybe we need to check our, this is going into our PicoSoC. So this is actually, this is a PicoSoC. Let me just double check what is on the screen. So this is, you see, 32-bit. I'm slightly not sure why this is only 4-bit. Maybe they didn't need so much more. So this is CPU. Let's maybe then open the, it's actually CPU definition Pico RV32 Verilog. So this is a real small RISC-V RV32i processor core. Actually, this is also only 4-bit. So this is address, write, and read data. And what is this? This is write strb. What would that be? Memory word size. A word size something, huh? So this is always begin word size. So this is either byte, byte or 16. So 8-bit. 16-bit or a full 32-bit, I guess. Register operand 2, memLA write data. So yeah, so this is apparently, as far as I see on a first glance, decoding. If it's an 8, 16 or 32-bit access, that certainly makes sense. And so next we need to, can close this again, PicoSoC, we can also close that again. So certainly we can for some part ignore this. So these are the signs of when you read a specification and it says writing non-word aligned data is undefined, or implementation undefined, whatever. It's exactly what we could do here, is ignoring this and say not decode whatever, and just always, maybe it's even not used here. Here it is. Here it's, so it's, if it's one, or so this is using the bit. So okay, actually, okay, this makes sense and is simple. So this is, the original code was just using these bits here, the 4 bits, to see which of those 8, this 4 times 8 bits of the 32-bit word to assign. Is actually quite elegant and makes sense. The thing what we need to change here is that so read data GPIO. So either this is read or write, and we don't have this GPIO. We have VRAM. So what we need to change, I copied this we need to change this so that we write into the VRAM, and our VRAM is 16-bit as per the previous video. So this would be something of read data, VRAM something, or actually not totally 100% sure if it makes sense to switch here whether this is read or write. But first we can synthesize this and see if it synthesizes at all. IO memory data but has no driver. Okay, now it's complaining that it doesn't have a driver. So read data. What another issue I had is, so let's first write this here completely. So read data, so this is only 16-bit. So because our VRAM is 16-bit, there you see where all the issues stem from in hardware design. We have a 32-bit bus and we have 16-bit memory, a 16-bit memory bus and a 32-bit data bus here, and we can certainly ignore this for now and have here, for simplicity, only support 16-bit read and writes for a beginning. Because why not? So this would actually no, VRAM. So this is a address meaning IO mem address something. So this is using the lower address bits. The lower how many address bits do we even have? We have some 8K. How many bits would that be? Would that be like? Let's check here with 2 to the power of 10, no, 12. So we have maybe 13 bits or something. And does that make sense? And this is even 16, as I said, 16 bits. So this would actually be like bit 13, these are bit 13 to 1 or something of that sort, because we would only support, need to think about this another day. Let's first see what happens for a start. Of course, syntax error, what are also missing that. Does it make sense, by the way, this many bits? 1, by the way, because we need to map to our 16-bit addressing. The first bit set would be 1, and if we keep like a 1-to-1 mapping of addressing into the 16-bit VRAM video memory, the first index, like counting from 0, 0, 1, 1 would be the second byte of the first 16-bit VRAM cell, if that would make sense. I have here one complication, except syntax error 444. What have I typed now? Right, here is our this is GPA. Oh yeah, let's see what happens then. So this would be read data, reading this. I have one complication is, so what is this now? Warning wire is assigned in the block. What does it want now? IO mem ready is assigned in a block. What does it want? Is this an output? What do we not have? IO mem ready. So this is a register. IO mem ready, and we pass this in there as an. Oh, wait a second. What do we have? So this is a register. What do we have it here? This is IO mem ready. We have this as output. So IO mem ready. Not really sure what it wants now. Clock input. SB IO in can only drive. So this is, by the way, most likely the error message we had earlier. So that is also undocumented. What happened now? Did we maybe intentionally, accidentally? Wait a second. What is other? This is only a comma. This is that. What is this here? IOMEM. This is commenting this in again. Why would that now fail? PLL clock input can only drive a PLL. I thought we fixed this. Slightly confused now why. This is the wrong clock maybe. Did I pass in here the wrong clock into this maybe? Let's see, VGA. I think I passed you. There you see what happens. This is the wrong clock signal. This is exactly the error that I was fighting the last hour or two. This was my original design issue, which I solved by using this other PLL building blocks there. Let's see comments in the audience. Pretty interesting stuff putting up here. Just came across your channel by accident. Really like this content. That is nice to hear. Welcome to this channel. Have to mention from outside point of view, it's hard to figure out what Arch has the biggest traction, ARM, RISC-V, PowerPC, or even MIPS. I would say, of course, PowerPC is only big in the server and embedded space, and MIPS is basically only low power access point embedded space stuff left. And of course, ARM is RISC-V is new, but I would say I think ARM is dead. Of course, ARM right now is big, but I see ARM can only decline. I think RISC-V, because of the open source nature, RISC-V will prevail, and we have in a decade or two, I only see RISC-V left, if not overtaken by another new different open source architecture. Okay, this is actually already what I was nearly expecting. So you see, hardware design is not easier than software, maybe even harder or something. I had this issue before and not really sure why this is happening. So this will most likely debug off camera, because I think it's too boring to live stream hunting this. The issue is that we run out of resources. You see, failed to place cell of VGA VRAM, a RAM of type iStorm RAM. And the issue is here, you see here our resources. We had something similar in previous videos. The issue is that our VRAM now consumes more space here, 146%. Actually, maybe we can simply fix this. For me, it's always puzzling. So maybe let's just use one bit less here, and maybe this fixes it already. What I don't like with users, maybe I need to check with Clifford about this. But maybe this is Verilog, because I had this before. It irritates me a little bit when I say I want a register. By the way, so this is our video memory, and I think this is a more modern way of having the synthesis tool automatically convert like huge areas of registers to memory. And that's also what it's doing here. It's converting this to iStorm RAM. And the thing what I don't like is, you see it's still huge. What I really don't like is when I say I want 16-bit of 4K, you see 4 times 1024. This is 4K, 4000 times 16-bit, so making this 8K. And so although we say this, it's because we most likely access more here accidentally here in this assignment, I guess, of I'm really wondering. Let's just make this even smaller. VRAM, is it even? Let's see, VRAM. So this bits. At least this is what my intuition tells me, that this statement here is generating more address lines to the VRAM registers of our random access area, that we run out of resources. You see, we have here 44 out of 30, 146%. And I had something similar already. The reason I know why this is happening is because I have something similar in using my text mode. This is why right now my text mode here, text versus graphic mode bit here, is not yet used. I have the same for the graphic mode case. So just by accessing here the if not text mode here for video mem, if I enable this statement, then I have the same issue. So not yet really sure what's going on there exactly here with this too many bits assigned of VRAM. So it must be exactly the same problem. And this is also the issue what we actually need here, because the next design issue with this is that we need to access our video, because we have the video signal generation running here. We need at the same time access our VRAM for read write, so it's like dual port. And this actually, so you see this is single normal as single port memory here for the system memory, and this is dual port memory. So right, by the way, this just became smaller, right? So you see we just decreased the bits we used here and this became smaller. So maybe this synthesizes even, but this for sure the statement is not yet correct. So we are all ourselves, after a little bit at university, which is a decade ago, which also was certainly at university, you oftentimes do not do such more complicated and involving system design stuff. You do some simple stuff and hey, now we are generating how many? So 36 out of what? 36 out of what the heck? Oh, we're not generating. Why is this? Was irritated. 120. Yeah, so whatever is happening here. I'm also not sure, because I have the same issue with graphic versus text mode, where I need to access the, actually no, it's not, so actually no, it cannot be, anyway. The other issue is that we need to make sure that Yosys is correctly generating dual port access, meaning that from both sides we have here our VRAM, here in our VRAM, our memory, dual port memory cells, like so, so. And what we need is we need our video clock signal generating, so we need to constantly read this, and from the other side we need to read-write this from the RV32. This will be the next challenge, which is why the video is always, why I do it off screen, and this takes an hour or two, or an afternoon or a weekend. And yeah, so this is the next dual port memory challenge here to solve. If you have tips for this, let me know. This again didn't synthesize because still not small enough. Maybe this is also what is happening here. So how many, but we are only addressing, I'm really not 100% sure what is happening here. Actually very, yeah, I mean, these are only a few bits, right? I mean, we could for a test, let's for a test use only 2 bits and see what happens. And we need to debug this anyway later and understand this in full detail. So comments the audience, macro writes, yeah, the pure fact that we now get hardware IP available, RISC-V and PowerPC from what IBM is making so much available, especially in the last year, that ARM business model is challenged. Yeah, I mean, ARM business model is mostly challenged by RISC-V. People already Western Digital for hard drives and certainly next SSD controllers. But even NVIDIA of all companies is adopting RISC-V for their power management stuff. And so, yeah, this, I see that the future for RISC-V is huge, and I see it used everywhere. Marco writes, he doubts Apple will ditch ARM processors, gladly accept diversification. OSs cannot handle, what I understand. Yeah, even, but you see Apple already ditched Motorola 68K, then they ditched PowerPC, and now they maybe potentially soon ditch x86. And if there is no ARM development in a decade, maybe Apple will ditch ARM. Never say never. Apple could also be as dissatisfied as I am and other people are with the state of Apple hardware and macOS peak bugs. Maybe people will even migrate away from macOS again. You see, so we only use 2 bits, so why would that be? how many bits is this wiring up? I mean, I would think this is, you know what, let's hard code this here for a try. Let's always use address 1. You know what, maybe this is connecting too many bits here. That this is connecting 32 bits, but I mean, it doesn't add up with that, but let's see what happens with just 1 bit set. More comments, something. Heard people call ARM CISC due to how complicated it is. Yeah, ARM, so I made some RISC, for those who are new to this channel, I made a dedicated RISC-V instruction set architecture and a video live stream and also a video comparing MIPS and Spark and all these details a little bit, always like as much as you can compare it in an hour. ARM, I wouldn't really call ARM CISC, but I agree, ARM is super complicated. Are we synthesizing or it's still, yeah, it's good that we have an AMD Ryzen 3950X here. Previous video is as long as it synthesizes. Maybe we need, I wonder, maybe we assign you so many bits. You see how long this is synthesizing. Unfortunately, it's mostly single threaded. Yeah, yours is 101%. Here of, what did I? Yeah, 4.2 gigahertz here, turbo boosting. Also need another cooler. 4x4 heights, ARM64 simpler, so we are apparently maybe not so, it still failed something, iStorm LLC. So now, okay, now it apparently didn't instantiate more memory. Now it instantiated a huge amount of logic elements here, probably as a memory replacement. Maybe this has to do with using here so many bits. How to write, either we could, how would that be, how many bits of, how to write the 16 bits of this, or what's this, maybe, so maybe combine 16 bits of binary 0, or hex doesn't matter for that regard anyway, hex 0, or something, comma, and the remaining 16-bit output of that. Maybe that is the issue. Maybe you can debug this. You can probably, there is, if you want to debug this, there's icebreaker JSON, and you can see some details here of connection stuff. Read multiplexing, fun stuff. You get the idea. 7,000 bits of something. Maybe there even, or most likely there will be visualization tools of showing you the logic element connections there of that. But that is something to explore another day. Oh my god, it's late already. Probably my wife is wondering where I'm on Christmas Day. Let's see here one final run of assigning this read data. Again, this is our 32-bit bus. Read RD data, read data. Yeah, 32-bit system I/O bus. Let's see how long this synthesizes. Otherwise, yeah, there you see, not making this up, that usually this stuff takes an hour or two of research before I present here the somewhat finalized result. And this is a learning curve, right? I mean, certainly similar to software development, you're not, the greatest software developers are not falling from the sky. Everything takes some years of studying, trial and error, gathering practice. I already see something is probably wrong. The synthesizer is too long. It's really funny that I also need to get more into more syntax. Why would that be? So basically, Here, okay, so right, the syntax is just this. So if we want to make sure to only use some bits, the syntax would be Z. So that would be access. So this should be address, and then how many bits. So basically like 16 bits like so, just to make sure, because I think we can cancel this already. If it runs so long, then usually it generated some 9,000 or so logic element stuff. Let's see, at least it doesn't syntax error out instantly, but also, yeah, maybe it's not generating the dual port stuff and it's generating some crazy stuff. I have no idea what it's generating, but something. Yeah, comments were Vorbev writes ARM64 is simpler. Yeah, I read they cleaned up some vintage stuff, because you should not forget ARM is also nearly as old as x86 from, I think, probably the 80s. It's probably quickly fact check that. Sorry, ARM when it was Archon RISC machines, probably in the 80s. I guess in 1985, 34 years ago. So this is also full with legacy stuff. And for ARM64, they actually removed quite some stuff. Yeah, you see it generates forever. This is, if you were wondering, do I make this stuff up? No, that I need a Ryzen. Although, yeah, for this, mostly you need single thread performance, which is not too bad on this. Probably there was a package, you probably only need to cool it better and see what are we here. 3950X was max turbo of 4.7 max boost, which I have the feeling we might not be getting. But yeah, this is, there you see how long is this stuff synthesizing. Yes, it's really synthesizing long, even on an AMD 3950X. There again, run out of resources. And exactly the same issue, so we need to further understand. So again, it still generated the same, so just apparently just this one access here is causing that. Let's put here another just for the test of it. So yeah, either need to ask there somewhere, just some test pattern, doesn't really matter, whatever. Just for a quick synthesizing test. Actually also not yet really sure. Warning wire, why is it still IO mem ready assigned in a block at VGA? Why is it IO mem ready? Why is this complaining about that? So positive edge of clock, I mean output. So yeah, this is synthesizing. Also, how many gates have we left? So we have some text core, text video core and text mode generation here for this amazing stuff. So we have still quite some logic elements left, so there is some hope that we can get some PS2, or maybe even if we are super lucky USB, not sure, but for sure PS2 and audio, so we will get some pulse width modulation stuff, and maybe this, we will see in a month or two if it makes a more amazing homebrew system than the 8-bit guys Commander 16 or what it is. Because this is RISC-V 32-bit, and let's see what graphic and sound we can get into there. So yeah, so you see this is how long it's synthesizing, and even though this is not what we want, so you've seen just I need to either guru meditate here really long over this, or ask some experts like the Icebreaker Discord there, or Clifford. But I also don't want to bother Clifford with each and every of my beginner questions here. But yeah, we are so close. You see it's running together here. As a summary, we have this now integrated Pico RISC-V here running. Let's let's reattach this. Yeah, so this is still running here, not making this up, and memory test passed with our video design and not making this up. If I unplug, okay, come here for the final proof that this is real. As soon as we unplug this, this will be gone. And so yeah, not faked here, this is a real thing. And yeah, we are so close and yet so far. Which by the way, let's anyway, yeah, that's mostly for today. We are so close of just wiring the read and write logic to this I/O bus, and yet so far and not yet understanding why the heck this is happening. I have totally no idea. Maybe we need to attribute it differently for a dual port memory. Maybe it's simply not generating a dual port memory the way I think it should. But yeah, something of that sort is how it should be written. I think we had here like something of so many bits here. So something of this sort is most likely how it should be. Just that, yeah, so this addresses of this I/O memory address and then those bits and the top bits. Yeah, because why will the top bits of a 32-bit read and write will be 0? Because otherwise we need 2 access cycles anyway. This would be too complex, and anyway then it's simpler to just have the top bit 0 and just force 16-bit aligned read and write there. That makes everything more simple. And when you were wondering, when you read specifications here, like what do we even, sorry, I didn't show that, download, let's show you shortly. If you were reading specifications like this in like Voodoo and whatnot, other hardware, and you were wondering why the heck do they only allow, like Voodoo only allows 16, I think the 3DFX Voodoo either only allows 16 or 32-bit. Actually, no, I think it was 16. So the Voodoo only allows 16-bit read and writes or something from the frame buffer, exactly for similar reasons, like why make it complicated, and if it hurts performance anyway and complicates the design, and just make it, force it 16-bit for example, or 32-bit and aligned like the RISC architectures, because otherwise just more logic gates and less performance and stuff anyway. So yeah, if you have any tips here for this video register access, maybe, but I think the recommendation was to like behavior, like use it like this registers. As far as I understood, the modern Verilog stuff use like registers here and have behavior analysis derive that this is a best synthesized as a block of memory. But probably you can manually instantiate this. That would be something of RAM here, some RAM cells. So you probably can, maybe it's, I'm not sure. But again, you also see here are the modes. So you can either have this as 256 something, different 2, 4, 8 or 16-bit as access modes in write and read. So this is the internal stuff in the uses, and maybe it came from Icebox or whatever this package was. Actually, we can fact check. Grab cells sim from, so this is uses here, so probably not, don't need to check where it's coming from, probably, yeah, uses. I think the recommendation was to just write it like human readable and have behavior analysis determine the implementation details, but maybe that's hurting us here. This also is a font, by the way, so this is 8-bit for the font, which by the way we most likely, maybe we changed this, not yet sure, because I will, for the graphic code to maximize, I said this in the previous live stream, to maximize here the text and video mode, I will most likely reuse this font here. Yes, hello. Here's my font here. To maximize the available video memory, I will most likely recycle this font, 8K font, second half of frame buffer. It's not yet implemented, so my thinking is, because for text generation we need to access the text video memory and the character set at the same time, or at nearly, actually, yeah. Actually, it's not really true, because it anyway has a read latency, so it's not really the same time. Maybe we can even make it one register area here, like one memory area. But my thinking was, because we need to read the text index and color attribute from the video memory and then look it up in the font memory, I somewhat thought it's like the same read and write cycle, but of course it isn't, because reading the text from the video memory is already a latency, so we anyway need to read it in the next cycle. So maybe we can make it one big frame buffer area after all, but if we don't, then my plan is to recycle this memory. If you switch to graphic mode, that's the second half of the frame buffer is coming from the character set area here anyway. So yeah, more homework to do, and of figuring out what's going on here and how to behavior analyze, instantiate here this dual port memory or whatever. Surely that is the issue, at least it is my educated guess of being a noob here and getting into this. But yeah, that's it for today. I hope you learned something and enjoy this as much as I do. Don't forget to share, like, and subscribe for all this fun stuff of Octane, P3, FPGA, and other product reviews, bits and pieces coming along here, and learning here for myself and you at home. That's it for today. I hope to see you soon for the next fun stuff to come. And yeah, hope to see you soon. Tuning back in for that.